Assalamu alaikum, my dear friends. In the past lecture we have discussed about the shear force and bending moment diagrams in a simply supported beam, but in this case we will take the shear force and bending moment diagram in a simply supported beam for this uniformly distributed load. This uniformly distributed load is basically the combination of the dead load and live load. The dead load is the load whose magnitude doesn't change with time, and the live load is that load whose magnitude changes or its position changes with time. So this W we have assumed as a statical load, and we are going to analyze this beam for this unit load W. But this is the W kilonewton per meter, that is uniformly distributed load over a length of L. So to design this beam, we have to first analyze this beam. For that, what we are going to do, we will apply the equations of equilibrium. That's summation V equal to 0, summation H equal to 0, and summation M equal to 0. That is, the summation of vertical forces should be 0, the summation of horizontal forces should be 0, and the summation of moment, that should be 0. Once these equations of equilibrium are satisfied, then our beam is stable. Otherwise, our beam will be treated as an unstable beam. Fine. So we are applying the equation summation V equal to 0. So after applying summation V equal to 0, that means the summation of vertical forces should be equal to 0, or in other words, I will say the summation of upward forces and downward forces should be 0. Since I will take the upward forces as positive, that is RA plus RB minus W over a distance of L equal to 0, or in other words, I will say RA plus RB should be equal to WL, that's upward forces should be equal to downward forces, because the downward force is small w over a distance of L, and I will treat that WL equal to whole W, that is a weight. Fine, downward weight. And to analyze the horizontal forces, I know the summation of horizontal forces is equal to 0. That's the HA plus HB should be equal to 0. Since HB is 0, because it is a roller support, and in the roller support no reaction gets developed, so HB is 0. And applying HB here, we will also get HA equal to 0. So both the reactions in the horizontal direction, that is HA and HB, both are 0. Fine. Now we will take the third equilibrium equation, that is the summation of MA equal to 0. If I will take the moment about the point A, because a pin joint, and for a pin joint all the moments are 0, the sum of moments should be 0, because it's a pin joint, and pin joint doesn't apply any reactive moment, and when there is no reactive moment, this moment force gets nullified and it becomes 0. Here, as in the past case, we will take the clockwise moment positive and anti-clockwise moment as negative. That's if we take the moment about the point A. That means we have the force RB into its central distance. It will try to turn the beam in the anti-clockwise direction, and we will take anti-clockwise moment as negative. Then we have the W over a distance of L into its central distance L by 2. That will exert a moment on the beam in the clockwise direction. And we have no other forces. So the sum of these moments, that is RB over a distance of L, and the W over a distance of L into L by 2, that should be 0. So if I see, this is the anti-clockwise moment, this is the clockwise moment, and after then that should be equal to 0, because for a stable condition the summation of moment about A should be 0. And after analyzing or solving this equation, we will get RB WL by 2, we will get RA WL by 2. Fine. Now we have to see the shear force diagram. If we will see at the point A, suppose this is the point A, on the left side of this we have no shear force, and at a point A just right, I have the shear force of WL by 2. So I will plot the shear force WL by 2. Fine. Now I will reach the point C. If I will see on the left side of the C, I have the shear force, that is WL by 2 minus W over a distance of L by 2. Fine. So we know the shear force is the unbalanced force. I will see how much unbalanced force will be applied at C. So we have WL by 2 positive in the upward direction minus W over a distance of L by 2, and if you will see, it will become WL by 2. Fine. So at a point just left side of the C, I have the shear force. I will solve the shear force at A, just right of it is WL by 2. Now I will go to the point C. Fine. At C, just left I have WL by 2. Fine. Minus WL by 2, that is 0. That is this RA minus W over a distance of L by 2. So this is the unbalanced force which will be applied at the point C just left. So at the point C just left, I have two unbalanced forces, that is WL by 2 minus W over a distance of L by 2, and the value comes as 0. So if we'll see at the point C, the shear force will be 0. This is the point which is called as the point of zero shear force. Now if I will go to point B, I have just left of this, I have unbalanced forces, that is WL by 2 minus W over a distance of L. So if I will see, I will solve this equation, my value will come as minus WL by 2. So at point B just left, my value will be minus WL by 2. So I will see just left, it is minus WL by 2. At point B just positive, I will see what will be the shear force after B, just on at the right hand side of B. At the left it is minus WL by 2. There will be the positive shear force of WL by 2. So after solving these two equations, my value will become 0. Fine. So at point A just left, my shear force is 0. At point A just right is WL by 2. At point C just left is 0, and point C just right, it is 0. Fine. So at point C just left and just right, the value of shear force is 0, and this is the point of zero shear force. And if I will see at the point B just left, my shear force becomes minus WL by 2, and at B just right, my shear force becomes 0. So this is the shear force diagram, and for this shear force diagram we can design the shear stirrups for a beam. Those are the ring reinforcement for a beam. Now after that we will calculate the bending moment diagram. If we will see at the point A, the bending moment is 0 because it is a pin joint. At the point C, my bending moment will be RA over a distance of L by 2 minus this W over a distance of L by 2 into CG distance, that is L by 2 by 2, that is L by 4. Fine. That is the moment of RA about C and the moment of this UDL load about C. So after solving these equations, I will get the moment as WL square by 8. Fine. Now I will see the point, what will be the moment at B. If I will see this is a roller support, moment will be 0. Still, to check my calculations, I will calculate the moment of all the reactions, that is RA over a distance of L minus W over a distance of L into CG distance, that is L by 2. So my value becomes 0. So we have seen that at point B the bending moment is 0, and at the point where the shear force is 0, my bending moment becomes maximum, and that is WL square by 8. And for this maximum moment, I design my longitudinal reinforcement for the beam, and accordingly the beam gets designed for both stirrups as well as the longitudinal reinforcement. Even on the basis of shear forces and bending moment, the depth of beam is calculated, and accordingly the beam is designed. Thank you. This was the lecture how to analyze a beam for a UDL load. We have calculated the shear force, the bending moment diagrams. How this shear force has arisen, this is a separate topic.